So I know Dr. Olson sent an email out about this earlier this week, I believe it was, and she just sent an email out a few minutes ago. Just a reminder that at 2 o'clock today, her husband, Dr. Tim Olson, will be doing a career talk about his work with hey, you're fine. They do a lot of stuff with space objects and tracking space objects and how they're using data science and artificial intelligence and those things. So he'll be doing a. I know he's talking to the artificial intelligence class at 12:30 today as well, but at 2 o'clock I'll be giving a presentation from last week. So I encourage you all to come. I think it should be interesting. He does lots of cool stuff. So anyway, I just want to make sure that put it out there. There'll be snacks too. So anytime we have an event, we have to have food, right? That's the way it works. I used to, haven't done it for several years, but I used to grade AP calculus exams in the summer. Not because I'm a nerd, but because I got paid. But you'd spend a week grading the free response questions for the AP exams. One thing that they did was they feed you. Oh my God. You'd have breakfast before you go, and then you'd go grade for an hour, and then there was a break with food. And then you'd go grade some more, and then there was a break with food. And then you'd grade some more, and then there was lunch with food. And then there'd be an afternoon with, it was just food all the time. So, anyway, any questions at all about anything? What were you doing? Got an exam Tuesday, right? Very excited. No questions? Yeah, I will get to those posted today. I just hadn't had a chance yet to do it, but it is definitely on the agenda for today. I will definitely go into these questions posted. I apologize, I haven't done it before today, so it'll get done. But thank you for asking. Yep. All right, so we're going to continue on and discuss these distributions we've been talking about. So last time we developed the exponential distribution. Remember your PDF for the exponential distribution using that parameter theta was 1 over theta e to the negative x over theta. It came about from having a Poisson process, but rather than counting number of occurrences in a unit time interval, it came about from looking at calculating the waiting time until the first occurrence of a Poisson process. So you need to be a little bit careful when you're reading problems. Just because it says that you have a Poisson process doesn't necessarily mean you're talking about a Poisson distribution, right? Poisson distribution is a discrete thing. It counts number of occurrences during a certain length of time or certain length of something, certain interval, versus still have Poisson process for exponential, but it's a waiting time. It's a time until the first occurrence. We should also identify what the support is, of course. Our x needs to be positive in this case, because if we think about it as waiting time, time has to be positive, right? So it needs to be greater than 0. Using the parameter this way, what's your mean? Writing the parameter as 1 over theta this way, with using the theta as the parameter, what's the mean? Theta, good. What's the variance? Theta squared. What's the moment generating function? Good. 1 over 1 minus theta t. Good. Okay. So those are the kind of the important pieces of information that you have for an exponential distribution. The relationship between the parameter for the exponential and the parameter for the associated Poisson. So let's say we have theta is your parameter for the exponential and lambda is the parameter for the Poisson that's associated with it. What's the relationship between those two parameters? The reciprocals, right? Your lambda is 1 over theta, or theta is 1 over lambda, either or the reciprocals of each other. Okay. So also an important piece of information in the problem, right? If it says you have a Poisson process with a certain number of occurrences in an interval, you need to make sure you remember to do the reciprocal for the exponential process, in particular for the mean and the variance, right? Okay. All right. Extending that, and this is what we started talking about right at the end of class last time, extending that from waiting time until the first occurrence to waiting time until the alphth occurrence, which just sounds really funny to say, okay, changes the distribution from an exponential to a gamma. Okay. in the book, they go through and derive why this was what the distribution should look like. It's the same idea that we did for the exponential. Let me scroll back up, see if I can find the work here for that. Had it in here somewhere. There it was. Okay, so remember when we developed our PDF for the exponential distribution, we wrote it in terms of the CDF first, right? And then converted it to a complement to say, well, if the waiting time is less than or equal to this is 1 minus the probability that it's bigger than this, which means there would be no occurrences in that interval. If you're doing the waiting time until, say, the 5th occurrence, you would do it in the same fashion. You would just say at this point there are fewer than 5 occurrences in that interval. Right? Rather than no occurrences, you would say there's fewer than 5, maybe it would be 4 or less. If you were saying you're doing waiting time until the 5th. We know from that perspective we'd have to do it as a sum from 0 to 4. There'd be no occurrences or 1 occurrence or 2 or 3 or 4. So you'd write this as a sum rather than the single piece that we had here for no occurrences. Right? And then, but you would do it in the same fashion. Write it as a sum and then do a derivative. The nice thing about that derivative inside the sum, nice is a relative term, I suppose. You have to use a product rule because you've got W in a couple of places. But the nice thing is it turns into one of those telescoping sums that you talk about in calculus, and it turns out to be a nice formula, which turns out to be the one that I mentioned down here. Slow scroll back down. I'm not going through it because it would take us probably a good 15 minutes to develop it, and I don't want to spend the 15 minutes on it, especially since I'm not going to ask you to redo it. Yeah, Kevin? Until if it's if it's past the first, you use a gamma distribution. So if it's second, third, fourth, it would be gamma. Okay, we're gonna do some examples of that today. Okay, all right. But in any event, if you go through all that stuff that I was just mentioning, you'll end up with this formula. Okay, I promise. They do it in the book for an integer. We talked about this last time, that if alpha is an integer, you get this as your factorial. In any event, the reason why that works that way is because you would use your integration by parts formula on this and just rewrite it in terms of a smaller thing. I will do that real quick just to show you that relationship. Let's go over here to the side. This one I actually like, so let's do that. So one of the reasons why I'm going to do this is because you need to know how to do integration by parts, right? So we'll let u equal the y to the alpha minus 1 piece, and your dv be your e to the negative y dy piece, right? Okay. What's your du going to be then? Good. Alpha minus 1, y to the alpha minus 2. Good. What is your v going to be then? Good. Negative e to the negative y. So then, using our parts formula here, we would have y to the alpha minus 1, oops, a negative, y to the alpha minus 1, e to the minus y. And then we'll have the integral from 0 to infinity minus the integral from 0 to infinity. Oh, let me move that over a little bit. I can pull the negative out, so that'll change that to a plus, right? We agree with that? That changes that to a plus. Okay. Pardon me. Pardon me, goodness. I can pull the alpha minus 1 out in front as well. And then I get y to the alpha minus 2, e to the negative y dy. You don't have to circle this in your notes. I'm just doing it so you can compare the two things. What's the difference between those two integrals? What's changed? Yeah, the exponent on the y now is an alpha minus 2 rather than an alpha minus 1. Right? Okay. Remember, this thing up here is gamma of alpha, right? That's how we define it. So what does this have to be? That's gamma of alpha minus 1. We've plugged in alpha minus 1 rather than an alpha up there in the exponent, right? Okay. We agree with that? Okay. So now let's go to this limit here. Yeah, I have a limit, correct? I've got that improper integral. I do have to be a little bit careful. I need to make sure my alpha is bigger than 1, otherwise I have an issue with doing this, right? A little bit of an issue doing this because it'll throw it in the denominator. But as long as alpha is bigger than 1, if I put in 0, we'll get 0, correct? If we put in infinity, that goes off to infinity, but what does this go off to? 0. Which one wins? The 0 does in this case, right? Because exponentials go off to infinity faster than powers of x or y do, right? If I move that to the denominator will get bigger faster than the numerator does. So that really does go to 0. So when we're done, we get the relationship that gamma of alpha is alpha minus 1, gamma of alpha minus 1. That's a cool relationship. It's what allows us to generalize the factorial function. Okay, we mentioned this last time that if alpha is an integer, then gamma of alpha is alpha minus 1 factorial, right? The reason why that works is because of this recursive nature. We would need to get down to a base case, if you will. Well, gamma of 1, if I put 1 in for alpha, notice that gives you the integral from 0 to infinity of e to the negative y dy, right? Because you'll get a y to the 0 power. We agree? Okay. I'm going to write a bad thing. I'll write e to the negative infinity. That's a bad thing, right? It's not a number, but it illustrates what I'm doing. What does this go to? That goes to 0. This is equal to 1. So I really do get 1, right? So the whole point of this is that when I get to gamma of 1, I get 1. So it really does stop that factorial at a 1, right? So I really do get alpha minus 1 factorial. All right. It's important to recognize that for some of these when you're writing down the PDFs. Okay, so let's go back to the example and see what I mean by that. All right, so here's the example. I know it was a lot of work to get to that point, but here's the example. Let's see if we can do a problem. Make this a little bit easier. Okay, we've got calls coming in at 2/3 of a call per minute. We want the waiting time until the 10th call arrives. Sorry, not arrives. Arrives. Poisson process, waiting time until bigger than 1 occurrence happens. Okay? That's what's telling you that it's gamma. Okay? All right, what's theta in this case? If I want gamma, I have 2 parameters, right? What's theta? 3/2. And what's alpha? 10. Okay? Alpha is the number of occurrences that you're trying to figure out the time until. Okay, so the alpha is 10. Your theta is 3/2. So if we want the PDF, then you would do f of x equals x to what power? Yeah, alpha minus 1. So in this case, it'll be 9. E to the what power?
So negative x over 3 halves.
Yeah, negative x over 3 halves, so I might as well write it as negative 2x over 3. We agree? Denominator? Gamma of 10. What is gamma of 10? 9 factorial. Good. And then the last piece is theta to the alpha, so it's 3 halves to the 10th. That's the PDF, right? Yes. Remember, that's the parameter for the Poisson, right? That's the lambda. The parameter for the gamma or the exponential is the reciprocal, right? It's flipping it upside down. That's where we get the 3 halves. Now, notice, this is fairly ugly to try to do any problems with integrals, isn't it? If you were to try to do this by hand with integrals, you'd have to do integration by parts 9 times. No one wants to do integration by parts 9 times, right? So if you were actually doing computations with this, you would always use a calculator or a computer to do it. You'd never do this by hand. Okay, that's stupid. That's a waste of everyone's time. So let me just show you real quick a couple of things. First, I'll show you Excel. Again, if you get nothing else out of doing math, know that Excel is an exceptionally great computational tool. It's an insanely good calculator, right? Okay. The gamma function is built in. You want, you have to be careful. The gamma here is literally the gamma function, right? So for example, if I wanted gamma of 10, we said that was 9 factorial, right? It should give me 9 factorial. So if I do factorial is also built into Excel, I do get 9 factorial. So the gamma all by itself literally is the gamma function, okay? If we want to do probabilities, we want the gamma dot dist function, okay? Notice what the parameters it takes in. I know it's hard to see because even though I have it zoomed in on the screen, the little helping thing doesn't help very much with being able to see from far away. The first thing you put in is the x value that you're interested in. The second thing you put in is the alpha parameter, which is the same alpha. However, instead of using a theta, Excel uses a beta here for the second parameter. Beta is theta. Okay? And then whether or not you're going to put it into the PDF or the CDF is that last parameter. So I know the problem didn't ask for it, but say you wanted, what's the probability that it was the waiting time until the 10th occurrence was less than 5? Okay. Well, then I would put 5 in for x because it was less than 5. But the alpha was 10. The theta was 3 halves. And I want the cumulative distribution function in that case. So I make that true. And then it'll spit out a probability for me. You can also use your calculator to calculate these probabilities, but you'd have to set up as an integral, right? So the integral I would have mentioned just a minute ago, if I wanted the, I'll write down the integral. The waiting time until, the waiting time is less than 5, then the probability would be the integral from 0 to 5 of that function we just wrote down. And then you could type that integral into your calculator. You can put it in your calculator, yeah. You're never, ever going to do any integral like this by hand. I would never do that to you. No one would ever do that to you. Well, I shouldn't say no one, but no one here and no one at a job would ever do that to you. That's those two things I can guarantee. Okay.
Where would someone do that to you?
Some sadistic math professor somewhere else. No job would ever make you do that by hand, ever. That would be a waste of time for the job. They want you to be able to calculate these things quickly, not slowly. Doing that by hand is slow. Say it again. So you would go in math and go into integral, and then you just type it into the different spots. Okay. All right. Are we okay with how this is set up? We're going to do a couple more examples, but are we okay with how this is set up? Yeah, no.
So the exponential is just the time until the first occurrence, but the gamma is the time until the selected one.
Yep. Yeah, that's exactly right. Yep, the exponential is first. Gamma is anything above 1. Now, the nice thing about the gamma function is that alpha doesn't have to be an integer, even though conceptually we think about first occurrence, second occurrence, third occurrence if we think about an actual process. This is used more for modeling things that die off eventually, and you might want to use a different alpha that's not an integer. Okay. So what I mean by that is if I go over and maybe plot a couple of these things. For example, if I plot the function x to the 9th, e to the negative 2x over 3, oops, and apparently my big fingers hit another letter, divided by 9 factorial, and then 3/2 to the 10th. Have to see if I can zoom my y's in a little bit more. There we go. It's a little bit better. All right, there you go. You can see it a little bit better. I had to zoom in really small. So you can see that these exponential and gamma functions are used to model things that die off eventually. But the exponential distribution, remember, just goes down like that, right? So as soon as you start off with some quantity to start with, and then it all just dies off all the time, this would be a better model for something that grows and then dies off over time. Right. And then you might want to play around with the different alpha parameters and the theta parameters to get to fit whatever data that you have. Okay. That's what these particular types of distributions are used for, is to model something that might grow quickly and then die off over time. Okay. Does that make sense? So the problems that we will typically deal with from a conceptual standpoint, it makes sense in our brain. We'll think about second occurrence, third occurrence, fourth occurrence, but it may be the pith occurrence, the cube root of 27th occurrence. Oh, that's 3. The cube root of 38th occurrences, something like that, right? It doesn't have to be an integer. You would use a parameter that makes sense for the context of the problem. Okay. How would you determine whether or not a parameter might make sense for the modeling that you're doing? Okay, let me just talk about that briefly, because that's an important concept later on if you're going to do anything with statistical modeling. Okay. It doesn't matter what you might be doing. You can do statistical modeling in engineering, you can do statistical modeling in chemistry, in physics, whatever, right? But let's go back over to this thing. We haven't talked about what the moment generating function and the mean and the variance are yet. Okay, so let's briefly mention that. I'm not going to derive them. You derive them in the same way that you would do the exponential like we did before. I'm just not going to take the time to do it. Okay. I'm just going to tell you what the moment generating function is. Notice again, we said that the gamma distribution is a natural extension of the exponential, right? What was your moment generating function for exponential?
1/1 minus theta t.
Good. It's the same thing, except that you're going to raise it to the alpha power. We could derive it using the same formulas that we did before for exponentials, or for expected values, I mean. We're going to have a much better way to get at this later on when we talk about doing sums of distributions later in the semester. So I'm going to save it for then. Okay. It'll make more, conceptually, it'll make more sense then than trying to just go through the brute forcing the expected value. Okay. However, from moment generating function, we can figure out mean and variance, right? We'll do our log trick. Remember our log trick to do that? Okay. If I do the natural log, the reason why we do the log trick, of course, is it allows us to break these things up, right? This is 1 minus theta t to the negative alpha. So I can bring the negative alpha down in front. That way? We agree? What's the first derivative equal to? What do you get for the first derivative? Good. The negative will cancel because when you take the derivative of the inside, you get a negative theta. So the negatives will cancel. How do we find the mean from this? Plug in 0. What do you get when you plug in 0? Alpha theta. Good. Now let's see if this makes sense. For exponential, what was your mean? Theta. That's the mean waiting time until the first occurrence, right? So let's say that the mean waiting time until the first occurrence was 3 minutes. What would you think the mean, just conceptually, what do you think the mean waiting time should be until the second occurrence? If it's 3 minutes until you see the first, it should be, how many until you see the second? 6. And in the third, it should be 9. What are we multiplying by? The number of occurrences, right? This should make sense. Right? Conceptually, it makes sense based off the exponential. How do we find the variance using this function? What do we do? Second derivative and plug in 0, right? Second derivative here, this is 1 minus theta t to the negative 1. When I differentiate it, bring the negative 1 down, make it a negative 2, and still multiply by the negative theta again, right? So we're going to end up with alpha theta squared over 1 minus theta t squared. And again, we'll plug in 0 and get alpha theta squared. Again, does this make sense with what we know for exponential? If alpha is 1, we get exactly what the variance is for the exponential. Does that make sense? By the way, again, I mentioned that we'll talk about the moment generating function later when we start talking about sums of distributions. What in the world just happened? Oh, it's turning in the whiteboard because I pushed the button on my pen with my head. Sorry. I put it in my head and turned it on. Sorry about that. This will also make sense, hopefully, when we get to that point. I've got a variance of one distribution. I've got a variance of a second distribution that I'm adding together and they're independent. So we should just be adding the variances together. That's a concept that we'll talk about later in the semester as well. I wanted to go back now about how you would use this for statistical modeling. Okay? What do I mean by that? If I wanted to use this particular function to try to model some distribution that I didn't know anything about, what would I need to do? I would need to take some samples, right? And get some results, and then try to use that sample to help me estimate what these parameters might be. If you've done anything with statistics at all using a normal distribution, you do that, right? You take a sample, you figure out its mean, you figure out its standard deviation, and you use those values for the mean and the standard deviation. Okay? The same thing would happen here. If I wanted to use a gamma function to model something, I would take a sample, big or small, doesn't really matter. I would take a sample and I would use that sample to help me estimate the mean and the variance, because I can calculate the mean and the variance of the sample easily. Especially mean, right? I can add up and divide by how many there are, right? I've got two equations and two unknowns, so I can figure out the alpha and the theta from that. Well, I'm sorry, I can't figure it out. I can estimate the alpha and the theta from that. That's what you do in statistics, by the way. You take a sample, you see what's going on with the sample from calculations that you can do, you use you use those values to set up a model, and then maybe you'll take other samples and see if they fall on that model and see if it makes sense. That's what statistical modeling does. And if that doesn't make sense, try a different distribution, try again. If that doesn't make sense, take another distribution, try again. Right. That's what statisticians do, in a nutshell. Okay. All right. This is why we care. All right. We don't care about the fact that these functions are nasty, because like I said again, no one's ever going to ask you to do these by hand. The idea behind this is we learn these different types of distributions to see if they make sense for what we're trying to model in a physical sense for whatever that process happens to be. Okay. All right. Let's see if we can do the next one. X has a gamma distribution. Theta is 4. Alpha is 2. And we want the probability that X is less than 5. Now this one you should be able to do by hand because the integral is not going to be too nasty. Okay. Yes. Say that again. On the exam, no, I'm going to want you to do the integral by hand. But I'm not going to give you a really stupid integral to do by hand. It'll be one that you should be able to do easily by hand. Well, relatively easily by hand. Depends if you know how to integrate or not. You're not going to have stupidly nasty integrals on the exam. I promise. All right. Although you should be able to do something like x times e to the x. You should know how to do integration by parts. Okay. All right. Gamma distribution. Theta is 4. Alpha is 2. What's the PDF? Let's start there.
X e to the negative x over 4 over 16.
Where'd the 16 come from?
Theta squared.
Good. The first part is, I'm going to write it down, but you've already simplified it. Exactly right. The first part would be gamma of 2, right? But what is gamma of 2 equal to? 1 factorial, right? So 1 factorial is 1, right? Okay, so this is just 1/16 x e to the negative x over 4. If I want the probability that x is less than 5, what are we going to do? Integrate from 0 to 5. Oops. This is one you should be able to do by hand. This is hopefully very transparently an integration by parts. X e to the x is something that you should recognize as a parts one, right? But we're going to let u equal x. dv is good, e to the negative x over 4. So your du is dx, and your v is good, negative 4 e to the negative x over 4. Good. I know I left my 1/16 there because I can just pull the constant out in front, right? I'll just do that. 1/16 times negative 4x e to the negative x over 4, evaluated from 0 to 5. Minus a minus is going to make a plus 4 times the integral from 0 to 5 e to the negative x over 4 dx. For which one? The original integral? No. Can't do it or use substitution on that one. I mean, I can make a u substitution to get rid of the x over 4, but then I'm still going to have a u in front when I make my substitution. So it's not going to help me. At some point, I have to use parts. The first piece here, if I simplify it, we put it in 0, we're going to get 0, right? Without any doubt. So we're going to get a negative 20 e to the negative 5/4 there. The next part, we're just anti-differentiating e to the negative x over 4 again. We already said that that was negative 4 e to the negative x over 4. Yeah? We agree? Okay. Now we put in 5, we get a negative 4 e to the negative 5/4 plus 4. On the end. Oh, goodness. Whatever that simplifies to. What? 1 minus, what do we get? 36 over 16 is 9/4 e to the negative 5/4. If I did my arithmetic right. Do I care if you simplify the arithmetic? Do you think I care if you simplify the arithmetic? No. You could have stopped here. This is fine. I certainly get a 16 here while I'm up on at 4, but I got a 1/16 out in front, right? And then I've got a minus 36. 36 over 16 is 9/4. So, of course, you could check my arithmetic relatively. I mean, you can at least give evidence that my arithmetic is correct by typing that in and making sure that it's between 0 and 1. It's a probability, right? It has to be between 0 and 1. Certainly not bigger than 1. Just make sure it's not negative. Hopefully it's not negative. Should be fine. Actually, I'm certain it's fine. The reason why I'm certain it's fine, that exponent is bigger than 1. Well, it's less than negative 1. The 5/4 is bigger than 1. E to the first is a little bit bigger than 2.7. That's 2.25. 2.25 divided by 2.7 is less than 1. So I'm certain that I'm okay for it's not negative. Yeah. Estimation helps. All right. Any questions about the process? The process okay? This is going the other way, a little bit going the other way. What I mean by that is recognizing distribution from moment generating function. I don't need to be able to do that to calculate mean and variance because we can do mean and variance from moment generating function by doing derivatives, right? We know how to do that, correct? But what derivatives don't tell us are what the PDF is, right? So the idea behind this is to recognize what kind of distribution you have from the moment generating function. Because again, the moment generating function completely determines what the distribution is, right? What kind of distribution do we recognize this as? It's a gamma, right? What's this value right here? That's the theta, right? This value is the alpha, without the negative, right? Because it should be a fraction, okay? So your alpha is 20, your theta is 7. Right? From that, we should be able to answer all 3 questions now. Let's do the easy 2 first. And by easy, I just mean quick to write down. What's the mean? 140. Good. What's the variance?
49 times 20.
Good. Those 2 were pretty straight. Like I said, by easy, I just meant that was fast to write down, right? If I know that it's a gamma distribution to start with, then I know what the mean and the variance are once I know the parameters. Yes? Well, I would use the negative exponent to flip it down, right? Yeah. Okay. What's the PDF going to be? That one takes a little bit more to write down, but it's not too bad. What is it going to be?
X to the 19, e to the negative x over 7, all over gamma of 20 times 7.
Good. So the 19 factorial would be your gamma of 20. That's exactly right. And the 7 to the 20th, that would be your PDF there. Just to remind again, what's the support? What does x have to be? Yeah, it has to be greater than 0, right? Because again, our kind of physical interpretation of this is waiting time or time until, right? So it has to be a positive value. Again, no one ever, I'm going to go ahead and just get out on that limb. No one is ever going to ask you to do any integrals that involve that function. Okay? Not by hand. Okay? That would just be cruel and unusual. Is okay? Again, this is why one of the reasons why we talk about moment generating functions is the fact that we can recognize the distribution based on the moment generating function. I'm going to skip this one for the time being. I don't care about that one. Let's do the next one. And the next one's it's just making a substitution. It's just a little bit more involved than I care about right now. This says that cars arrive at a toll booth 5 cars every 10 minutes. And then it says that we want to find, it's a Poisson process, so that's our clue that something is either going to be a Poisson, an exponential, or a gamma, right? Something along those lines. And then it says, find the probability that a toll collector has to wait longer than 26.3 minutes before collecting the 8th toll. That 26.3 seems oddly specific, right? Okay. We'll talk about why that's oddly specific here in a second, which is going to lead me into the next thing. Let's just start with, what are we doing? What kind of distribution are we talking about if we're looking at waiting time until the 8th toll? It's a gamma, right? If I have a gamma distribution, hopefully the first thing that I can do is identify the alpha and identify the theta, right? That's what I want to do first. Hopefully alpha is pretty easy to identify. Alpha is the number of occurrences you're looking for. So what is alpha in this case? 8, right? Because it says collecting time until the 8th toll. Sorry, waiting time until the 8th toll. I don't know, I looked up and saw the word collecting, and so I said collecting instead. Okay. All right, theta. They tell us Poisson process with a mean rate of 5 cars for every 10 minutes. What's your theta? 2. Good. It's reciprocal, right? That would be 5 over 10. The reciprocal of that's going to be 2. So your theta is 2 in this case. Good. Pardon me. All right. Let's write down the PDF, and then we're going to talk about how this is an example of a special type of gamma distribution. Okay. What's the PDF?
X to the 7, e to the negative x X over 2.
Okay. Over.
7 factorial times 2 to the 8.
Okay. Good. All right. Notice that in this particular distribution, your theta is 2. Okay. When your theta is 2, and your alpha is even, we get what's referred to as a chi-squared distribution. Chi-square distribution. Do I want alpha is even? Is that what do I mean that? Let me be careful. I really mean even. Yeah, the alpha has to be even in this case. Okay, I'm okay with that. Anyway, the idea behind that, I'm not convinced that I mean even. I may have to go back and change that word. What I mean from a chi-square distribution, there's a special form, all right? In particular, this is 2, without a doubt. That's what the chi-squared part comes out, all right? The other part for your distribution, something has to be even because I have to divide it by 2. Well, that's not true. I think I'm lying to you. Anyway, doesn't matter. This is what the form looks like. I might be just completely lying to you, and that's fine. All right. Everywhere else, there's this R over 2 spot where your alpha is. I don't mean that alpha is even. I mean alpha is equal to R over 2. The R part is even. Doesn't matter. All right. No, the R doesn't have to be even either. Alpha is... Ignore that part. Just kidding. Yeah, just ignore it. I was thinking the even because of the divided by 2, but that can turn out to be a fraction. That's okay. It's always going to be either an integer or half of an integer. Okay, the R will be an integer. All right, that is for certain. R will be an integer. This is a chi-squared distribution. This R value that we have here, don't worry about why we call it this yet. This is more of a statistics topic. The R value is called the degrees of freedom. Okay. The notation, if we has a chi-squared distribution on R degrees of freedom, is chi-squared of R, like that. So you use the Greek letter chi, put a squared on it, and then of R. My apologies about the whole even thing. My brain was not working correctly, which is not anything that's different from any other day. All right, the chi-square, we will see some applications of the chi-square distribution later this semester. If you do any statistical analysis, if you're familiar with, say, ANOVA, analysis of variance, you use a chi-square distribution. Chi-squared pops up a lot in analysis, in statistical analysis. It's a very, very, very important distribution. It's probably, it's up there with normal. I mean, normal is the end-all, be-all of distributions, but chi-squared is up there. Okay. All right. Anyway, let's talk about why this is an oddly specific number. Okay. If you were going to calculate this, what integral would you set up? If I want the probability will have to wait longer than 26.3, I want the probability that x is what? Greater than 26.3. Setting that up as an integral, what would you write? Yeah, 26.3 to infinity of the PDF, right? right? Again, complicated as an integral, right? However, if I recognize right away that this is chi squared of 14, I might have a little bit easier way to do this, okay? One of the easier ways to do this is using what's referred to as the chi-squared distribution table. And I handed that out last time. You should have that paper that I handed out last time. So let me explain how the table works. Okay? You're always either going to use a table or a computational device to do these things, right? You're never going to do these by hand. Okay? So how does the table work? So notice I give you two pictures. This should be shaded in a little bit better here, right? There's shading here or shading here. Those are complements of each other, right? Okay. So this is telling you, this particular expression is just telling you how you would get the CDF of this function, this PDF, this distribution, right? You're not ever going to calculate that integral. It's just telling you that's what the CDF would look like. These are the values, though, for your CDF calculated for various degrees of freedom that are going down the left-hand side and for various probabilities that you're looking for. Okay? So what I mean by that is if I wanted to know if you had a chi-squared with 5 degrees of freedom, which would be that row, and I wanted to know what the probability was up until x equaling, or sorry, I wanted to know when the probability was equal to 0.1, I would look at that column, because that's where the 0.1 column is, and find out that my x associated x value is 1.6. Okay? Those are kind of percentiles, right? That 1.61 would be the 10th percentile for a chi-squared distribution with 5 degrees of freedom. Okay? Now, the subscripts here are telling you about the probability on the tails. Your subscripts are these probabilities on the end. Okay? So the 0.1 is the probability for your CDF. The 0.9 is the complement. And in a lot of problems, if you've done any type of statistics, again, you kind of look at the tails, right? You want the tail to be small if you're rejecting a hypothesis. If you haven't had statistics, you can ignore the words that I'm saying, okay? Because you haven't talked about that yet. But you want the tails to be small, which is why they're doing the probabilities on the tails, okay? So let's go back and look at the problem that we're doing, and then let me come back to this table. Notice the way that we have this set up. It's set up as a right tail, right? Yes. Oh, crap. It is chi-squared of 16. Thank you. Why? Tell me why. You're right.
Because
It's 2 to the 8th. That's the r over 2 part, right? I was looking at that one. That's r2 over 2 minus 1. Thank you, Nick. Appreciate it. It's the r over 2 is here. I forgot the minus 1 on the exponent on the x. That's why the r is 16. Yeah. Okay. This is asking us about a right tail problem, right? Okay. So let's go back to the table and figure out how we use it to answer this question. Okay. First off, and with Nick with the assist there, what row should I be looking at? 16. I need to look at this row, right? Now, I want an x value, I want a probability. It's asking me to calculate a probability. These aren't, in this row, aren't probabilities. Those are x values, right? The probabilities are up in the top, okay? However, what x value am I interested in? 26.3. I told you it was an oddly specific value. I would have recognized that I made a mistake when I got to this one. Okay. Do you see 26.3 in that row? Yeah, it's right there, right? There's our 26.3. Now remember, we're trying to figure out a tail, a right tail, right? Notice above, I've got 2 probabilities essentially given to me, right? Which one's the right tail? The that 0.05 is the right tail, right? The subscript is giving you this probability in the right tail, and that's what we want, right? We want that above a certain point. So going back to our problem, the answer here is 0.05, roughly. Yes. What part about it? Because the reason why is because it says we want the probability is greater than, and so that's giving us on the right side, the right tail. If it were less than, then we would use the 0.95. Okay. By the way, you could have also done this, of course, in Excel. Always, right? We've got, notice there's even a chi-squared distribution right tail. Also, these chi-squared inverse and chi-squared inverse right tails. I want to talk about both of them here. Chi-squared distribution will give you a cumulative distribution up until a certain point. If you want past a certain point, you would use right tail. That's what the RT stands for. Okay? So let's just do that to see that we really should get the 0.05 like we saw from the table. The x value is 26.3. The degrees of freedom is 16. That's all we have. I did put a comma. That's all we have to type in. X and degrees of freedom. The reason why, the alpha is always, the theta is always 2 for every single chi-squared distribution. Okay, so I don't have to worry about putting in a theta. All right? I get roughly 0.05. And this is a table of approximate values, right? We could also go the other way. Let's say I wanted my right tail to have a probability of 0.05. This is where they're getting those values in the table from, by the way. I want the probability in my right tail to have 0.05 with 16 degrees of freedom. What value should I see when I hit enter? Which is what I see. That's where they get those values. They're the percentiles, right? That's the inverse question, correct? So, like on your homework, one of the problems asks you for the 40th percentile of a chi-squared of 9. If I want the 40th percentile, I'm going to use that, and I want to do it on Excel because you're not going to do it. I mean, you can, if you're clever, you can do it on your calculator, but it's going to take a while. I would use, if I want a percentile in Excel, I'm going to use that chi-squared inverse. Okay. I could use the right tail, but I have to do one. I have to think about it in my brain and do 1 minus, right? Because percentile is accumulated up until that point. Okay. So you use your chi-squared inverse. You'll put what the percentile value is. So say you wanted the 75th percentile, I would put 0.75. And then just put in how many degrees of freedom. So let's say we had a chi-squared with 18 degrees of freedom. Then the 75th percentile is 21.6. That's it. That's how easy it is to do on Excel. Yes?
What's the degree of freedom? What does that do?
So, trying to speak broadly, the degrees of freedom basically has to do a little bit with how big your sample size ends up being when you select a sample. It's not quite a one-to-one correspondence with that, but that's what it has to do. The higher your degrees of freedom, how do I want to say it? I don't want to say it wrong, but I don't want to say it more complicated because there's a whole discussion in statistics about it. The higher degrees of freedom you have, the more accurate your information should be. So if you don't have a lot of freedom, you're probably going to be off more often than not. Say it that way. So what I mean by that is if you've done anything with confidence intervals, the bigger the sample gets, the tighter your confidence interval gets. So the bigger your sample, the more degrees of freedom pops in, and so you're starting to get that tighter and tighter. So what I mean by that is if you've done anything with small sample sizes, you use what's referred to as a T distribution versus a normal distribution. Once you get bigger samples, that T distribution gets more and more like a normal, and so things get tighter. So the degrees of freedom gives you better information. But if you have to use your sample to estimate parameters, you lose degrees of freedom. So then it gets bigger. So that's kind of where that freedom part comes in. You want bigger samples if you can get them because it gives you tighter information. But sometimes sampling is hard. It may be expensive to do lots of samples, right? For example, how do car companies test safety of cars? What do they do to test the safety of cars? They crash them. That's expensive, right? You're not going to want to crash 10,000 cars to get a big sample, right? So you're going to crash a smaller number of cars, and that gives you fewer degrees of freedom. So then your analysis has to put that into it. That's where the degrees of freedom part comes in. Like I said, that's more of a discussion for a statistics class more than us. That's what we call it for right now. One thing that we will see is that you can generate a chi-squared distribution from sums of normal distributions. And so then the degrees of freedom turns out how many normal distributions you add together. So that there's a tie in there, and we will talk about that more later in the semester. I'm very, very good about talking about, pushing that off to later. We'll talk about it later. All right. This okay? Not too bad? See if we can do another one with a chi-squared here. Yes? Why did I keep the formula for gamma? I don't know what you mean. This one? Because the chi-squared distribution is a special form of the gamma. It's just the theta is equal to 2, and your r is an integer. That was what I was trying to say earlier. The r is an integer. It's a special case of the gamma. Every chi-squared distribution is a gamma distribution. The theta literally is 2, yeah. The theta is 2 as a chi-squared. And this value here, well, let me point here. This value here is either an integer or it's an integer over 2. Okay. Every single time. And also, by the way, your mean and variance also follow the gamma distribution. And your moment generating function does too. So your mean, your theta is 2, right? Because remember, your mean is alpha times theta, right? Right? In this case, your alpha value is r over 2, and your theta is 2. So we just end up with r. Every time. So whatever the degrees of freedom is, that's your mean. For your variance, that's alpha theta squared. Well, your alpha still is r over 2. Your theta now is 2 squared, and you get 2r. Your moment generating function is 1 over 1 minus theta t. Theta is 2. Your alpha is r over 2. So you get those same pieces of information. The big thing to remember, and I'm sorry I messed it up earlier, but hopefully messing it up will help you remember it. Chi-squared distribution, your alpha is r over 2. R is an integer. I was thinking alpha being even because I was dividing by 2, but that's not true. I hate lying to you. I don't do it on purpose. All right. Let's do the next one here. This is just a practice with the table, basically. So chi squared of 17 See, I think I have this on. No, I don't have it printed out. Do I? No. Chi-squared is 17. I want to go to the chi-squared distribution. Let's see if I can. No, I can't because it's embedded. Go back over here. Chi-squared distribution. Erase these other markings. What row I'm interested in? 17. Good. I'm here, right? That's the row I care about. All right. I'm going to have to flip back and forth. I apologize. First, part A. Is that a left tail question or a right tail question? It's a left, correct? Okay. So looking over here, this is the x value that I'm interested in, the 7.564. So I go back over here. Well, let's go back over. Actually, go back over. I want to look at my row, and I want to find 7.564. What left tail does that correspond to? 0.025, right? We see it? Because that's the value that's up here. Okay. So go back over here. Part A will be 0.025. What do we do for the second one? Okay, the right tail. I'm looking for which value again? 27.59. Good, 27.59. I want a right tail in this case, so what value do you have? Yep, 0.05. Good. Why do I keep doing that? How about part C? What would you think to do part C? If, let's say you didn't know it was chi-squared and you were going to start this problem, what would you do? How would you set it up? Okay, you could do an integral. Sorry, let's say I had say I knew the CDF. Let's do it that way. If I knew the CDF, what would you do? Good, exactly. You're exactly right with the integral, by the way. Yep. But I was thinking CDF. That was where I wanted to go, right? Because I want to try to use this table, correct? I can rewrite it that way, can't I? The CDF at 27.59, CDF at 6.408. Oh, I got 24 from 6.408. Yeah. Okay. So going back over to my table, both of those are what kind of questions? Left or right tail? Left. Good. So left tail associated with 27.59 is 0.95. With 6.408 is 0.01. So it have 0.95 minus 0.01 gives me 0.94. Is that okay? The last two, notice in the first three, they gave us x values and we're asking for probabilities, right? These are asking us for x values given probabilities, right? Still using the table, though. It's not too bad. This first one, we want the chi-squared sub 0.95 of 17. Remember, this is a right tail probability, so really what we're looking for is the 5th percentile, right? Remember, that's the complement. Okay. But going back to my table, that one's a pretty easy one to find. I just need to go to the chi-squared 0.95 column and get what x value. Yeah, 8.672. Good. And then the last one, we go to the 0.025 column. What x value is there? The 31.19. 30.19. Yep. Not too bad reading those off the table, is it? Not too bad. Okay. Tables, of course, were created before everybody had, a supercomputer in their hands. That's where all the tables come from. Tables are still used, of course, on certification exam ideas because they don't want everybody to be able to program things into the little supercomputers they have in their hands. Okay. So it's one of the reasons why we go through the tables. Of course, we could have answered all these questions on Excel, right? So just to remind a little bit of that, those last ones, those were, notice the way the last two problems were phrased were as right-tailed ones, right? That first one was chi-squared sub 0.95 of 17. So we would want the x value associated with a right tail probability of 0.95. That's what the inverse idea is, right? Rather than having an x and finding a probability, you're doing the inverse question. You have a probability, you want to find an x value. That's why it's labeled as an inverse. Okay. I could use the right tail inverse here. That probability was 0.95 in the right tail, and we had 17 degrees of freedom, and we should come up. Was that what the value we had? Yeah. I forgot which value it was. You should come up with the same value that we had, right? And then likewise, the other one. But you could have also done it as a left tail probability, right? I could have done it as a kind of a pure percentile idea. I just would have needed to change my probability to 0.05, and I get the same answer. The reason why they have the two different functions built in, it seems kind of unnecessary, but it depends on what kind of statistical test you're trying to do or how you are trying. A lot of this is making hypotheses and seeing if you can reject a hypothesis, so you're finding what's referred to as rejection regions. Sometimes your rejection region's on the left, sometimes your rejection region's on the right. So that's why they got a left tail and a right tail. Okay. It's not horribly important for what we're doing now, but I'm telling you why there's two different functions that seem to do the exact same thing. That's okay? All right, so as far as your test goes on Tuesday, I will get some practice problems put up on Moodle today so that you have those. We did those discrete distributions, right? So you've got all those discrete distributions. The continuous distributions, the ones we've actually named that we've done so far are the uniform, the exponential, the gamma, and the chi-squared. So those are the four that we've done. Make sure that you know your PDFs. Make sure you know how to find the means. Right? You know all those formulas like you're on the sheet, right? And don't be surprised when you see the first page is going to be just writing that stuff down. Okay? The memorization part. Okay? Okay. So just the PDF, the mean, the variance, and the moment generating function. Okay. If you're good at memorizing, you should have a good first page. If you're not good at memorizing, I'd make some flashcards and see what you can memorize in the next 5 days. Yes.
You said moment generating function too?
Yeah. Yeah. Okay. It won't look different. I mean, it'll look a little different because I typed it up, but it won't look different than that sheet just has blanks for you. Okay. Also, a big thing too, make sure that you remember what type of distribution is measuring what, right? Because that's going to be important for selecting what you're doing in the problems, right? Is it counting? Is it measuring? What is it counting? What is it measuring? That's important for being able to figure out what distribution to use in the problem. Okay. Those are the two big things I would concentrate on as far as studying concepts. The others will be just trying to solve the types of problems that we've done. Okay. All right. See you Tuesday, if not before. Don't forget, 2 o'clock, the other Dr. Olson is talking about careers. So have a good one.